What do you mean by the term comparator, John?
A comparator is such. So let's just do a simplified comparator. This is an operational amplifier. It is an amplifier. Okay, let's say it's anything. Let's say it's an NE part. Let's say it's an LM part. It's just an operational amplifier that you're going to set up to switch. In other words, its plus input and its minus input is going to look at a reference voltage and the voltage on the capacitor and say, switch. Dump that right now. So one way to do that is to look at, now that depends too, I don't want anybody to make a mistake on whether you're using, you know, a comparator that's inverted or non-inverted. Because that makes a big difference in where it's going to switch. It's either going to switch up to the positive or it's going to switch down to the negative. So the appropriate parts must be chosen to allow that switch to occur, and then tell the FET transistors to dump this charge.
So does it matter whether it's positive or negative?
No, as long as you have the correct device
Okay.
in the output or the end.
Yeah, okay.
Okay, because there's PFETs and there's NFETs.
Okay.
Okay, I would prefer that you'd use an NFET, so you want this thing to switch up to the positive.
Okay.
All right, so you want the capacitor to rise, and right when it gets to the time point that you have chosen. So the way you do that is by what you do with these inputs. Mm-hmm. You put a reference voltage, say here, of 5 volts. Now that's lock solid at a reference voltage, 5 volts. And you build a divider at this end between there and ground, and you're allowed to choose, by turning a potentiometer, you're allowed to choose when this is going to trigger. So you adjust this, and the comparator will go up and down, discharging the capacitor.
Okay.
So now, therefore, you don't have to have a commutator. You don't have to have a push-button switch. It's going to do it automatically. And by the number of FETs that are in the output, because they can all be paralleled, is the amount of current that you can pass through the machine.
Is that
Because
FET?
yeah, FETs.
Okay.
Yeah, FET, F-E-T. And the thing that you want the most is you want a high voltage FET that can do at least 15 or 16 amperes, each one. Because remember what I said here, and that was a very good question, Pat, because what I'm going to use is 60,000 microfarads
Okay.
when I do this.
Okay.
And the machine is quite capable of switching the 60,000 microfarads. And when you see a analog amp meter go hit 5 amperes or 4 amperes or 2 amperes or 3 amperes, you can bet that the peak is in the hundreds of amperes that battery is going to look at. But that's such a low impedance that what you're doing is you're whacking that battery. Now, that moves into the theory of what Tom Bearden talks about, back popping the battery. All right? And that means that you're coming along and you're hitting that battery with a pulse and you're giving it some time to rest so that it can absorb this. Mm-hmm. But what is this pulse? It's current. And what does the storage battery want to charge with? It wants to charge with the form of current. Very important to remember that it's current that's going to force this battery to charge. Okay, now after that, it gets conditioned to accept these discharges. And so Tom Bearden's theory is this. we sort of understand the comparator now, and we might have to go back over this. But these are all questions that can be answered, you know, at a different time. But Tom Bearden was very unique in what he said. That we have the plates of the batteries. We have a positive and we have a negative. So, in one direction, you're moving the lead from the positive plate to the negative plate, and when you recharge, you're moving the lead back. All right, so it can go either way, depending on what's going on with the battery. So when you're drawing energy out of it, it's moving one way, and when you're putting energy back, it's going the other way. But the thing that people really don't understand is that the battery can't perform two functions at the same time.
So you mean it can't be charged?
Well,
and
it
charged?
can only be maintained.
Mm-hmm.
So an example of that is your car. And I'm going to be very adamant about this. Is you have a 12-volt battery in your car. And that 12-volt battery is just the starting battery. You start the car, the alternator comes on, charges the battery to a maintaining voltage. Mm-hmm. Well, now, why do I say that? Why? Because your headlights are on, mm-hmm. Your ignition's running. All the energy is being supplied by this battery as if it was just a capacitor in a circuit, meaning that it's holding it level. Okay? You can never charge the battery fully in your car because the battery can't perform this dual function. So, what ends up happening with the battery? This is exactly what ends up happening with your battery, is the red lead falls off the positive plate and goes to the bottom of the battery until it builds up on the plates, like this. If we expanded this out, you've only got little trays in the bottom of the battery. And by the way, those little trays are time.
Okay.
This is the amount of time that you have life in the battery, is the distance from the bottom of the plate to this little tray. So, I think if you look at the batteries, you might have 1/8 of an inch in some of them. Walmart's a good example of that. Walmart battery.
Okay.
Okay, you have 1/8 of an inch, right? And so when you do this, you start the battery, and the function is for the battery to try to move lead to deplete the sulfuric acid and turn it to water so that there's no more charge in the battery. So that means that now the lead is moving from one way to the other way, right? So now the generator comes on and tries to push this back, but, oh gee, my headlights are on.
My AC's on.
Yeah, my air conditioning is on. My brake lights are running. My computer is running. Well, the battery doesn't know what the hell to do.
Yeah.
So what it does is it starts shedding lead. And these trays start to fill up. Because now you're trying to force a charge one way while you're discharging another way. And so the battery's having a hell of a time trying to maintain. So that's why when you turn your car off, the battery is sitting at 12.25 volts. It never got charged. Because if the battery really got charged, it'd be sitting at 13.20. It would be trying to sit there. But it's going to come down to 12.65. That's about where it's going to stand. All right? So now that you know that you could never charge your battery in your car because you were trying to do two things at one time, you might think about a different way to do this. Mm-hmm. Okay? So here's the thing. Back to the comparator, now that we explained a little bit about what you're trying to do with the battery. Tom Bearden said that the ions are big. And I'm sort of doing this expanded. I'm not an artist, but I'll do my best. Okay? And so when you charge this battery, you want to push these ions. So the first SG machine is a high potential, which is a spike going to the battery. Mm-hmm. And what has to happen here is all the electrons have to pile up. And as soon as they get the charge on them, they're going to move. And they're going to continue to move. So now you're charging your battery for a minimal amount of current. But you're waiting for what, Pat?
I don't know.
Time.
Time, yeah, time.
Time charge. That is a time charge.
Yeah.
So now we know that. But now let's take this a little bit further. Let's not use this spike. Let's say we can force this with current.
Okay, so we're in phase 2 now.
Yeah.
Yeah.
Let's say we force this with current, right? So what we do is, instead of it taking time for all these things to build, right? Mm-hmm. They're immediately there with the current. Very quickly. And they're moving. Mm-hmm. And they're moving very quickly to the next plate. So we're charging. So that's why I chose to have a primary battery and a secondary battery, because you cannot perform the two functions at one time.
Okay.
You see, if you can perform the two functions at one time by tricking it, then you can't recharge the battery. Then it starts to burn out equipment. Mm-hmm. An example of that was Jim Watson and his machine, which was basically my machine. You know, it was never Watson's machine because Watson didn't make it.
Right.
He only copied it. Of course, he got the money and I didn't.
So soon.
Yeah, one day. So the thing to remember now is what we're going to do is we're going to show you these three functions. So some of the questions that I get asked is, how can you charge the battery if there's no current? See, I mean, that's a known thing, right?
Yeah.
Remember I said that no matter how we look at this, right, what is actually charging the battery? Current.
Right.
And if we have little current, it's going to take this amount of time.
Okay, yeah.
And if I have forced current, it's going to take that amount of time.
Yeah.
You follow me?
Yeah.
And if I have pulse current, it's going to take that amount of time. So see, if you force the current, it's going to take less time. And if you pulse the current, it's going to take a little longer time because the battery has to absorb the charge to move the ions. And if you used radiant current, that's just the spike in the normal schoolgirl, right? It's this time, but it's a time charge. It's a charge that's spread out over time, and the longer time that the battery takes the charge, the better the battery is.
Yeah, so that
Because you're not overheating.
Yeah.
The forced charge is an overheater.
Yeah.
The pulse charge is a little bit better because it's breaking away the sulfation. But the forced charge is not doing anything. It's like your car alternator. It's just forcing the battery to charge. You follow me? It's not breaking anything up. This charge over time is going to give a little bit longer run time to the battery, where this one's going to charge a lot faster and this one's even going to charge faster. But if I can't break any sulfation up, because sulfation is going to happen no matter what happens. The idea is that if I have a window and it's clear, and I can see everything through the window, that means I don't have any sulfation. And that means that the charge is going to go there and it's going to be there. But if I start getting sulfation, I start to block the view of the window. That means that now the battery is losing its impedance. In other words, it's gaining a high impedance because this is a sulfate. It's a crystal that's on the plates, and actually when you look at it, we'll look at a side view here. Let me just move this a little bit. Is if this is a clean battery plate and I have no sulfation on it, that means I have no mountains like this. See? And this is a sulfation that you have to break up. And when you break this up, it comes off the plates and falls to the bottom tray.
Yeah.
I had and I may be way off base here, but where does stair-step charging fit in all this, or doesn't it?
Okay, yes it does. That is, I gave you the example, and I probably should have. John's capable of making mistakes, so. Stair-step charging is the way that the comparator is charging. So what's happening is it's as each pulse comes up, the capacitor is rising like this. I drew it on a linear curve. I just said this.
Yeah.
And I said that I was able to choose my time where I wanted it to discharge. Well, the stair step is the same thing, because the SG machine is a series of pulses like this. So each time a pulse comes in, the capacitor rises a little bit more, and a little bit more, and a little bit more, and a little bit more. But still, it's the same as this, because I can choose my time. So it's a nice term. It's easier for people to not get confused and just look at it this way.
Yeah.
Even though when you look at it with the scope, there's little steps in here all the way up. You understand what I'm saying?
Yeah.
Yeah.
So I always called it stair tip. You're stair stepping it up.
Yeah, we did a DVD on it at the conference. Yeah.
Yes, we did.
Yeah.
And we actually showed it on the scope.
Yeah.
Okay, so I think it's time to show you the three basic functions and how they work and what the battery is going to do. Let's basically start with the SSG motor, which is a simplified schoolgoer motor. Actually, it's very complex because on this one you see two fans, and the reason that there's two fans here is I need a certain RPM that I want to do this with. So I've actually added more drag to the motor so that with a normal motor, it would burn more energy. All right, and once again, I'm going to point out it's a multi-strand coil. We went through that on the board where, and if I can get Tony to come here, you can see there's multiple transistors all arranged. Remember I said 12 ohms here? And you can see each diode's on the output, and all the base resistors are underneath here, which is kind of hard to see. Okay. So there it is, right in front of you. And what I'm going to do with this...
And you said that green one was the trigger one?
Right, right. So what we're going to do is go over here to the computer, and I'm going to tell the computer to load this at 1 amp, this battery, which is sitting, by the way, remember what I said about if you had clear windows in the battery. It's a 13 amp hour battery, and the voltage is sitting at 13.2. So it must have been a full charged battery. All right, so we're going to start this test, and the computer is going to come up here and show you that the 1 amp is loading it. And we'll do this, you know, pretty quickly, because I'm going to pull the 1 amp, and then I'll stop that, and then I'll show the charge curve. Is how it charges up with the radiant, which is just the spike charge.
Which battery are you charging?
And we're going to charge this battery right here. So we're loading this battery right now on the West Mountain discharger. And it's a constant current charger, so as the battery falls down, okay, and if you look down here at this scale, it's telling you the amp hours.
So right now this battery's discharging.
It's discharging right now. You see the curve falling downward?
Yeah.
What are you discharging it into?
Into the West
okay,
Mountain.
that's the load.
That's the load, and it's
Which is what, a little fan? Or?
Yeah, it turns on a fan because it's generating heat. It's draining the battery.
Just a big resistor, is it?
Well, it's more than that. It's a linear regulator.
Okay.
And it's a semi-conductive device that's drawing it down. And see how this battery's under this 1 amp load is sort of now finding up a level. See
right.
it? But if you look very closely, it's stepping downwards. See it? So it's stepping down as it goes down.
Yeah. That's not just an artifact in a software program.
Well, it could be. It could be the computer, but it's stepping downward. So it's losing energy. See here, the battery is considered dead at 12 volts. And this is actually technically all you have to work with the starting batteries between this 12 volts and this level. So it's not very much to work with before your battery's dead. Okay, so now we've taken this power out of here at 1 ampere. And I'm going to stop that because I want to show you it go, how it charges now under the radiant load. Okay, so now if we stop this, and it gave us the voltage over here, we're at 12.46 volts, see? So to make this, to show you this, we'll start a new test. Okay, so now my lead battery is here, and I'm going to come back, and I'm going to call this test 2. And I got a lead acid. And I'm going to show you the charge monitor. And I'm going to start. Okay, so now we can see that we've started right here, right? See it coming along? So the battery's sort of recovering by itself. And now what I'm going to do is I'm going to hook up the SSG. And I'm going to give it a spin, and we're in mode number 1, basic number 1 there. Now watch.
Oh.
This is the basic spike charge. So we're watching the charge. Now we're really not charged fully until we're at 15 volts. See how it's charging? Now see, it's starting to rise. As soon as it hits 13 volts, right? It's going to start to rise faster than that, and the chart will change.
Okay, thank you.
Well, there's no current involved in this one. And then when we move to the next mode, which I'm going to, we'll force the charge. Okay? And then we'll move to the pulse mode. But I want you to see the basic that it does charge the battery. And it's doing it. And it's doing it pretty quickly.
Yeah.
So there's no reason why people are having trouble running out of primary power before the battery gets charged, unless they're doing something absolutely wrong.
Yeah. So this is coming out of this battery?
It's coming out of the machine. The primary battery is the trigger.
Right.
So we can actually monitor what the primary voltage is.
Okay.
Okay, see, the primary voltage is 12.44, and look where this voltage is, 1407.
Yeah.
So you can already see the gain.
So look at it suddenly skyrocketing.
Yes, because it's going to go up on its plateau, and we'll stop it. And then we're going to discharge it again and go to the forced mode to show you the difference in the curve.
Okay. Okay.
Now, we're going to change circuits here, right? Mm-hmm. That's going to go up to 15, and you're going to see how the battery curve actually looks. And it's going to follow the book completely. Mm-hmm. It's going to be right to the book. Okay, so the forced charge now, this wire is going to be removed, which is this black wire here.
Okay.
And it's going to be moved down here. And it's going to be in generator mode, then it's going to work just like a generator.
Just point out which.
We're going to move the wire from going back to the positive down to the ground now.
Okay.
And that's the red. So there's a real good looking battery curve. Mm-hmm. And look where the voltage is, Tony. So see, it can push that battery really quick if the machine is set up correctly.
Right.
Okay, we can stop this curve here, so we'll stop the machine. All right, because we're already at 15 volts. Now look,
Yeah.
that the battery falls down to its level of where it's just going to sit and rest.
Okay.
So look, here is 12, about 12 and a half, there's 13. So look now, after the radiant charge, the battery, remember what I said on the drawing about Tom Bearden's theory about piling up the electrons. So there's a high potential now with the battery. Mm-hmm. And it's showing that, because here's 14 volts and look where it's sitting. It's sitting about 13.8. But it's going to fall down as the charge bleeds off. Mm-hmm. So this was time.
Right.
And that didn't take very much time. Mm-hmm. And of course, where is our primary battery now?
12.71.
Yeah. How did it get to 12.71?
It went up from 12.44.
Right. How did it go from 12.44 to 12.71? Simple. There's a back charge that comes from the machine that also adds some to the primary each time it collapses. Okay? So now we'll stop this test, because now we actually have this on the camera, right?
Right.
And we'll go back to the test and we'll say new again.
Okay, so what?
Okay, so anyway, what we're going to do is now discharge this battery at about the same amount of time at 1 amp hour. And again, of course, you can see the charge coming down. But if you notice something this time, it's a little bit different with the radiant charge. It's staying a little bit higher, see it?
Yeah, maybe.
Yeah, it is.
And now what we're going to do is this, right here. We're going to force the charge after we take this down. See, it's dropping now after being charged that way in a little bit different curve.
Mm-hmm. It's more of a city
Yeah.
curve, yeah.
Remember, before we came down like this and we were down here.
Right.
And now it's taking a little bit more time to discharge because of the time charge.
Mm-hmm.
We're going to let that come down just a little bit more. And then we're going to go to the charge monitor. And we're going to do the force charge.
Okay. And then what was the last charge again?
Pulse.
Pulse charge, right.
Yeah. Comparator discharge.
Okay.
Or what everybody would term stair-step charge.
Mm.
And what we're going to do with that is we're going to show you, we're going to vary the times and the amount of power that we want to dissipate.
Okay.
It's quite a bit different, isn't it?
Mm-hmm.
Yeah, it'd be neat if you could have them side by side, all three. Showing it that way. And
Well, I think we can.
yeah. Now it's leveling off quite a bit.
It's got a much denser, compacted charge.
How long are we doing this for?
Well, we can. I'm just trying to drain most of the potential charge out. See,
Yeah.
because this is staying a lot longer than it did before.
Mm-hmm.
So that's a pretty good example that the charge is much denser.
Mm-hmm.
So that's the basic first function of, and we'll just stop here. Okay, and now what we want to do is we want to go to charge monitor. And we'll just call this test 4. Okay, so now we can see where the battery recovered to after the discharge, right? Now, this is very important that you watch this hookup, because there's two ways to do this. The first way that I'm going to do it is going to be just with a forced condition, as if the SG machine was a generator. So let's go over here. And we would disconnect this black lead from the Energizer, and we would insert this diode in line. To isolate. So now you got one going this way and one going that way. See? Because it's on the negative side. So now we're just going to start the machine. Now the machine's going to change pitch here. Now look at the forced charge. See, I'm forcing the battery to charge now in a generator mode, and look at the machine's speed. Now it's an actual generator. And look at the way this is going. Remember, I drew that on the board.
Yeah.
And it's forcing it. And what that is current, everybody. Now look at the primary battery voltage
1237.
and listen to the machine. As it approaches 14.97. It's already at 15 volts. So it's already boiling the battery. And so we'll let this approach. It's already there, so we'll let it go to 16 volts. And we'll stop the charge.
Is it 16 volts?
Yeah, it's at 1630
1630.
right now
Yeah.
with a very quick charge.
Yeah.
Now see, the battery can't absorb any more. It's just wasting in the chemical. So it's going to flatten out. Okay, so we'll stop this. We don't need to take any more from it. And now look at what the forced charge, where it's going to come in and settle. Now what we did was we took the amp hour out, or we used an amp hour to show you that it went down, and we showed you under a forced condition what the charge looks like, and then where it's going to settle off here. And now we're going to take another amp hour out for about the same amount of time, right? And then we're going to do the comparator discharge.
Yeah, and this is going up again.
Yeah. So that rose pretty quickly, that particular charge. Okay, so let's take, do you want to catch this? So we're settling out somewhere around 13 something. And now we're going to take the amp hour.
1394.
Yeah. We're going to take this, and now we're going to discharge it back at 1 amp hour. And we'll call this test 5. And now we'll have a completely different discharge curve because we brought the battery up higher yet.
This is the next circuit coming up.
Yes, this is number 3. This is number 3. This is comparator discharge. So we're going to use the comparator, and we're going to discharge.
And what's this again?
Capacitor.
Okay.
So we're going to use 60,000 UF microfarads. And that's going to be these 4 caps. So now this arrangement's a little bit different hookup because this comparator is going to discharge on the negative terminal of the battery, the minus, and the positive is going to go directly to the positive of the cap.
Okay.
Okay? So this is going to sense the capacitor voltage. Okay? And it's going to tell this when to discharge, and what you're going to see here is it blink a green light. And it's going to be this same arrangement with the diode in line here. So what we're going to do, now what we're going to watch this because this is negative, or negative of the battery over here. See, black. And then this is going to be negative of the caps. And what we're going to do is remove the positive lead and put it to the capacitors. And then we're going to take the positive of the capacitors, go to the batteries, And we're going to put a current meter so you can watch the pulses and how we're able to change the time period and how much power we're going to get. So we're pretty close down to where we were. So let's start a new test and watch the charge. So we'll test 5. And now we're going to go to charge monitor. Let's call this test 6. Okay, and this is where our battery settled in. Okay. Okay, and as you can see, our settling voltage is back at 1278. Right? Now we're going to start the machine, and we're going to stair-step it up with capacitive discharge. Now, as you can see here, each time it discharges, it's dumping. The meter's slow, so it's actually more than that, but that's meter's showing us about 3. Now watch. And look at the charge curve.
Yeah.
What are you seeing, Tony?
Stair steps.
Okay, now watch me change the rate. Now watch as I change the time to like lower seconds. As I build up more charge, I build up more current. See it?
That's that spike, is it?
That's what you're listening to is each time it discharges into the battery.
Yeah.
Now look at,
Oh yeah.
So why is that happening?
that's the stair step up. That's the time that it takes to charge the capacitor and the comparator.
So why is it stair-stepping more now than it was when they...
Because
more
I've
current
changed the
coming
time to like once a second, see it?
in? Oh, okay.
And it's over 4.5 amps. If Tony looks at the meter. Actually, it's a lot higher than that. So, once again, by viewing this, right, we'll let this run till it gets to 15. And we're stair-stepping it up, but that's about once a second.
Yeah.
And so the machine is charging 60,000 microfarads of capacitance.
It's not growling, is it?
No, no, it's relieved of all that,
Yeah.
of all the stress.
Is this 3 or 4 now?
Which one?
We're on 3.
Still, are we? Okay.
Yeah.
It's suddenly climbing up rapidly.
Yes.
So it's more like a forced charge now? Or
No, no, no. No, the voltage is rising and the current is going down. See? Because the battery is not requiring current now. You're right at 1533. See, now it's going to start to bend over.
Okay, because it can't take any more, right?
Right. The chemical can't
Right.
absorb it. And
15.5.
Yeah.
15.5.
now, let's just show this one time. Let's just show the rates here, Tony, of our comparator. So as I go this direction, I'm going to increase the rate, and you can see that here.
Right.
But I'm going to decrease the current, see? Because I'm not letting the capacitors charge as high. So I could choose any time scale that I want.
Yeah, look what's happening on the...
Yeah, if you look at the curve, it's totally different. Here it's 16. Now watch as I increase. As the battery absorbs more charge, the meter reaction will be faster. See? See how fast it's going?
Yeah.
Yeah.
Now if you remove the diode from this, if you remove the diode, then we're under a different mode. See? Because now we're not isolated. So there's where I removed the diode, the little
Right.
notch, and now it's continuing to charge. And now watch the adjustments here. See, I can hold it steady at 1.25 amps,
Yeah.
or I could move the machine into a much,
Dropping off.
yes. Why? Because it's not isolated, and it's not a forced charge. It's a
Okay.
capacitive discharge. But yeah, but it's dropping off at 16 volts, so it's boiling
Yeah.
away. So basically, those are the operations of the machine. And once again, I want to point out to you that with that device, you can choose wherever the time.
And that's what you were doing with the little adjuster?
Yes, with
Okay.
the little adjuster.
Right.
And that was in this little circuit like this. And I was tuning this
Yeah.
little pot.
With this thing.
Yeah,
It's like a little mini screwdriver.
yeah. And I put the green light here so that you could see the flash rate of how quickly the comparator switches. Now, it's very important to remember this is not a normal comparator circuit. It's much more sophisticated, all right, than what we've drawn.
Right.
So, and it's something that we built. So, you know, they can, if they need to have this comparator, the thing about this comparator is if you feel this, Pat, you feel a heat here. Here, come here. You feel the heat here.
Oh, yeah.
Okay, that's because each time this 60,000 microfarads dumps
Can I
the
touch
charge.
these?
Yeah, absolutely.
They don't feel hot.
No,
It's just that.
and either does the coil there, Phil. Now, I want to point out when the machine runs right, you can hold these devices. Here, Pat, do you feel any heat?
Uh-uh. No.
It's at room temperature. So when you build the machine correctly, this is what your machine will do. And depending on how many amp hours you're going to take out of this battery is dependent on how much time it's going to take to do what we just did. So please don't change things. You know, if you have one of these machines, because it's already calculated for this device and for these kind of batteries. In other words, don't come up with a little bitty battery and expect it to do what this battery does or this battery does. Now, as you can see, that's the primary energy that we've used compared to what our energy output is. So if we do this long enough, we can get a gain and we can get a COP rating. So now if we disconnect this,
It starts jumping up immediately.
right, right, because it's recovering.
Right.
It holds it in a locked condition, and it's going to maintain that current level no matter what you do. And so you can see here that our ending curve is about 14.2. It's going to come down. You know, it's going to come down to the level where the battery wants to sit. So basically, Those are the three modes of operation of the machine that's not fully understood. And now it should be very well understood of what you can do with the machine once the machine is put together right. And once again, I'm going to point out no neomagnets. You don't need them. It's not going to help you. It's going to hinder you. Don't make any alterations on the circuits. That's going to hinder you. It's already been figured out that this is where it runs. And you can see that it runs with all these different devices hooked to it. What I thought I would do is recap all these circuits, and starting with the simplest SG, and basically this number one circuit was the original schoolgirl motor, with the exception that the recovery diode and the secondary battery was not there.
Okay.
So basically this is exactly what all the circuitry was that was in her little motor. The only exception being that she used a small signal device transistor, a 2N5885, instead of the bigger power transistor. And in the second circuit, which has never been a part of the projects from the original SG circuits that are on YouTube. So all variations of the SG circuits on YouTube are nothing more than this circuit here. Okay. The very first circuit as you've seen it draw, as it's drawn right here. All right? Now, one thing to point out is this circuit has never been shown until now.
That's the forced charge circuit?
That's the forced charge circuit. And this circuit has really never been drawn or shown, or the values ever shown till now. In other words, the comparator circuit is a totally different circuit. The way I build it, there is a company building one which is licensed by me.
Okay.
And if you have to run a comparator circuit, then I would suggest that you start out with this basic controller that's built by Eric and Tom Childs and John Korn, because this is going to allow you to do a lot of different things that will allow you to protect it. It will allow you to try many different experiments, and plus the circuit's given to you.
Okay.
So if you burned it out or did something like, you could repair it. My circuit, I'm going to tell you right now, that is basically a heavy-duty circuit, and I'll just grab it and basically bring it into view here. And in the one that Energetics built, there is no protection because we don't want any protection in it. But the only reason that we haven't released it yet is there's not an understanding of how to work with this circuit yet.
Okay.
And this is what I'm trying to bring out here, of what has to be done.
So this is the same as this one here?
Well, this is the same as what we're using right now, right? And the only difference being is there's 4 large capacitors, 15,000 microfarads each, and they're in parallel for a total of 60,000 microfarads, which is a lot at 80 volts, if you bring it up to 80 volts. And so, of course, you see 5 FETs at 16 amps each in the back of this comparator. And that's located right here, as we explained it. This curve here allows you to adjust the trigger level at the voltage that you want. So what you're actually adjusting to the secondary battery is the amount of current that the battery is receiving under charge.
So that is a much more simple one of these.
Yes, this is very simplified
Right, okay.
compared to what I was just showing you.
Yeah, okay.
The one that Energetics builds, which you can purchase if you want,
Mm-hmm.
is potted, and you adjust it one time to wherever you're going to use it.
Mm-hmm.
And it's not made to put a power supply into. It's made just for the SG machine. So,
So last night when you were adjusting this, this is all going to be potted, so you wouldn't be able to make those micro
no, you can
adjustments?
make the adjustment.
Okay, you can.
That's left so
Okay.
that you can do that.
Okay.
I'm just telling you that there's no warranty on it,
Yeah.
because we have no control if somebody's going to put a power supply on it.
Right.
So therefore, there's no guarantee on it.
Right.
It operates when it leaves here, and what you choose to do with it, you do with it.
Mm-hmm.
So you may purchase it from Energetics if you need it. And so basically, these are your 3 circuits. Circuit number 1, Schoolgirl Simplified, Revision A, dual transistors, all the way up to 30,
Okay.
if that's what you need to do, and then the comparator circuit. Now, one thing I'm going to point out to you is these arrows indicate the phase of the device. So everybody knows that you're going to need a positive signal to trigger this transistor on. At that point in time, it's going to pull down because it's inverted here. So down here is drawn a little phase splitter explaining to you a little theory of how this is actually operating.
Yeah, okay.
And as the coil flips around the other direction, then the discharge occurs and the voltage goes to the battery. However, if you choose to make a massless current, then you would find yourself with a resistor in here, and then you'd be summing this like you see right here. Mm-hmm. And then this would be a delta 0. And what you would see is a signal that's just spikes. Now, point out again, in red, do not use any neomagnets in any of these motors, because if you do that, you're going to saturate this core, and you're not going to get the same as what John got here on the bench. Do not make any changes until everything runs. A good starting point is between 680 and 470 ohms on the basis of these transistors. You start there.
Okay.
Don't go too low and don't go too high, because you want to be in a range where the only adjustments that you're using is exactly what you've seen in the motor on the bench over here, which was a series resistance with the base resistance right here. And you saw my series resistance was 12 ohms. And that was to balance out the motor to get the highest speed with all the devices. Now, the kit circuit board is also, you may purchase that. Mm-hmm. And also Eric and Tom Childs builds a simplified version of this.
Okay.
So that you can start out with a basic machine. But basically that's the kit circuit board. And that covers the things that you didn't know about the SG. You did not know about 1, 2, 3, or 4. All right, and there's nothing that covers it better than the way I'm doing it. Mm-hmm. Because this is the way I want it to run. This is my concept of it. And so, who knows better than the inventor of it? And so, basically that's what I have. Right here. And do you feel to need to do anything else here, Pat?
Not really.
I think you covered the bench stuff pretty well already, John.
Yeah.
So
Is there anything? Oh, one other thing to cover. Very important. And so I'm going to let the camera get a shot of this. I'm going to back out of the way, and then I'm going to erase this.
Okay.
And I'm going to show you the way that the motor, the condition that this motor is actually running, and I'm going to explain the difference between the two.
Okay.
Okay, what I'm going to actually do is show you a top view of the coil. I'm going to put two of them here. Okay. This kit motor is running in a traction, which means that the magnet is being attracted to the iron.
Okay.
So it's being triggered before
That
time.
magnet's on this wheel.
Yes, it's on the wheel. So it's actually regaging itself because it's being attracted in, and then the coil flips over and you get the discharge. So if the wire is coming out on the right-hand side at the top of the coil, then it's a repulsion motor. It's a repulsion. And if it's coming out the left-hand side of the motor, it's an attraction motor, which means
Top, right?
the North Pole's being attracted to a south field.
Okay.
So it's being pulled in. But remember one thing too when you're doing this, that the magnet can only be attracted in halfway. And then after that, there's no more attraction. It
Okay.
just goes by. All right? So if you have an SG machine and you want to run it in a traction, right, all you have to do is if you wound, look at the top of the coil, and if it's clockwise, just reverse the two wires and then reverse the trigger wires.
Okay.
So we'll take a look at that in a second. And then you can put it into a traction. A traction is the most efficient and the less heat on, there is no heat then on these devices, so you don't need a heat sink on them.
Okay.
When you're in repulsion, you're forcing this, and it takes current to do that, and these are going to get warm on you, and so you need to heat sink them. Because otherwise there's no heat on this motor.
So this is wound counterclockwise.
Yes, it is. It's wound counterclockwise. And if you look at the top of the coil, there's an arrow on the top of the coil.
Yep.
And you can see that it's coming out of the left side. So this is an attraction motor, this kit. It's not a repulsion motor. And I wanted to clear that up, that the attraction mode is more efficient because you get a higher percentage of torque on the wheel because the magnet's being sucked into the iron.
Okay.
So there's like a little extra benefit there when you're doing this. And I wanted to make sure that you understood that.
Yeah, yeah.
The difference between attraction and repulsion. And so if you got a normal SG and you want to change that, and we'll just blow this up. And you have a north magnet here, right? And then of course your coil. And you've wound this. And the easiest way to test that is by taking the battery. Just take a battery and just tap it with the magnet near the pole. And if it's in repulsion, right, it's going to want to push away.
Oh, okay.
So then hold the wheel back a little bit so that this portion, and I'll put this in red, that this portion of the magnet is now here. And then when you tap the battery, and if it sucks it in, it's in attraction. So that's the difference. Now, one other thing to point out to you is if the coil's already wound and you want the motor to be in attraction, and it's really in repulsion, just reverse these two wires along with the trigger coil, and it'll be an attraction. So you don't have to rewind the coil. It's just that the left-hand side will come out down below instead of at the top.
Yeah, okay.
These coils happen to be wound so that it came out on the top. On the machine that we wound them on allows that to happen, but you don't have to do that. Just wind it left hand instead of right hand.
Yeah.
In other words, you're going to wind clockwise or you're going to wind counterclockwise. If you wind counterclockwise, you're going to be in attraction. If you wind clockwise, you're going to be in repulsion.
Yeah, okay.
And that's basically what I wanted to bring out.
And what were you saying about the trigger something?
Well, if you reverse, the trigger is wound along with the power coil.
Yeah, because you mentioned.
So you have
last
to
night
reverse
one of
that
these
too.
Trigger wire, and I didn't quite understand that.
Yeah, one's the number 23, right? It's the small wire.
Okay.
And one's the large wire, which is a 20.
Okay.
All right? And you see two different colors there.
Yeah.
I think you see blue.
There's a blue and the rest is red.
Yes. So the red wire is the power coil and the blue one's the trigger coil. And if you want to reverse this motor between repulsion and attraction, when you reverse the power coil, you have to reverse the trigger coil too.
Yeah, see it.
Okay?
Yep.
So basically that concludes what I wanted to tell everybody about the phases of this machine.
Okay. Is this copper wire?
Yes.
And the blue is what, still copper wire but painted?
Yes, it's just a different color so you can tell the difference between
gauge wire?
the trigger and the power coil. Because they're all wound together on the same thing.
Right, right.
There's all these different colors of wires down here. Green, red, blue, see?
Yeah.
You know, copper color. And it shows up real well when you do this.
This always goes this way?
Nope, the machine can go either way. So, and if I start it this way, right, then my fan is blowing air. And if I do this, it's sucking air. But it goes either way, the same speed, no matter what. Right. Yeah, and the reason that I have a double fan on this is because I needed a certain speed. I didn't want it to exceed. And so I'm forcing it to slow down because it actually has to blow air through the machine. So when I start it up this way, right, it's blowing air that direction. And if you go the other way, see here, let me give it a good spin and you can see it's actually blowing air. Okay, and then if we go the other direction, it's actually sucking air and blowing it the other direction. So, and another thing to point out too is there's 21 magnets around the wheel. It's an odd number to break up something that's being even. And we don't want even pulses. We want odd pulses.
Why?
Why do I want them?
Why do you want odd pulses?
Because I want to break it up. I want it to not be uniform. I want it to do, see, these aren't spaced exactly even each time. So it sort of breaks up the wave. And it so happens that the wheel's diameter, right, allows you this much time between the next charge and discharge. And it happens to be 21. It works out to be the best here.
So these aren't spaced, so...
Well, they're spaced identically all the way around, but there's 21 of them that fit this wheel, the diameter of the wheel. And I want that because that gives me an uneven number. And the machine seems to work better with an where they're not even, they're uneven.
So if it were a prime, say it was 29, Would that work better because that's a prime number?
No, I don't think it has to
Okay.
do anything with prime numbers or anything like that. It just seems to work very well with this 21 arrangement. You know, which purely, normally I would have spaced them all even, all the way around in building a test model. But it just so happened that this worked out, the spacing was 21, and it worked real well.
Yeah.
So we're not going to change it.
Right. Right.
You know, we're
No,
going to
I'm
go
just-
with
just
what
curious.
works the best.
Yeah.
So, and then the other thing was that winding these, we wound them on a lathe.
Mm-hmm.
So that's where we get the counterclockwise, because we're winding over the top of the machine instead of underneath the machine.
Whereas if you were winding them from a drill, it would go.
Well, you can change the drill because,
Oh,
but the
yeah.
lathe,
Yeah.
you follow me, is going this direction.
Right.
So the lathe is actually going clockwise when you're winding it, but it comes out to be counterclockwise when you end.
Right.
And that worked out really well, was the attraction. You know, and sort of it's a sort of a regauging effect. Sort of almost like a regauging motor. And so therefore, if it's being attracted in, it's not requiring any power. It's not requiring the transistor to push a lot. It's being attracted in for free, like that.
Yeah.
Then it goes past. And then it fires and attracts the next magnet in. So the devices run much cooler when you do that.
So really, you're inviting people to participate in a research.
Yeah.
Yeah.
Exactly.
And you pay
It's
to
all
play.
about research.
You pay to play, right?
Well, you do.
Yeah.
You know, it's part of learning about the machine, but I was sort of surprised that nobody picked up on any of these variations. Nobody tried to force the charge, nobody tried to do this, nobody tried to do that. And if they did do it, they didn't talk about it. So, and it's not mentioned anywhere, these 4 stages of the machine.
Yeah.
So I'm just happy that I could explain this thing once and for all. Because there's been a lot of questions, Pat.
Yeah. Yeah. I think maybe some people don't even realize that they're part of a research. They think, he says I can make this motor, it'll work.
No, you can't just make it.
Yeah.
You know, there's a lot behind this machine that needs to be studied, right?
Mm-hmm.
Now, the one thing about it is that you could make this far bigger.
Mm-hmm.
You could actually do it with a Ferris wheel if you could get a big enough coil.
Mm-hmm.
You know, and then once you do that, you have the mass inertia of it, which adds power to it. And you have the capability of having a gigantic coil, which gives you a lot of voltage.
Right. The quality of the wheel isn't that.
No, it's not important.
Right.
And it doesn't make any difference if this is a steel rim. The reason we want a steel rim is so the magnets stick to it, and then when we glue them and tape them, they're not going to move.
Right.
But it could be a wooden wheel, it could be a rock, it could be anything. It could be plastic. And basically that's your workings of the SG machine.
So what is the difference between this smaller wheel and that big Ferris wheel?
Nothing, except the circuit.
But on the Ferris wheel you had 2 of these things.
Right, I had 3 of them.
3? Okay.
That's the Bedini-Cole circuitry, which is the bipolar circuitry.
Okay.
But that could have very well been this circuitry.
Okay.
There is no difference in the wheel. The wheel, just because the wheel was bigger, right?
Yeah.
It still used all north poles around the wheel. So it could have been done either way.
Yeah. Okay.